Hey, John here. Let's talk about multi-threaded applications. All right, now the way these things work is you have multiple threads, and I'm going to illustrate it in the standard way by drawing what is essentially a picture of a piece of thread on a paper here. All right, this is a drawing of two threads called T1 and T2. And what these are going to do is they're going to collaborate to solve a problem in a divide and conquer method. All right. So let's say I have this big array with 1 billion elements in it over here. And my job is to sum them up. Do I write a program that just says a loop that says for, I equals 1 to 1 billion or 0 to 1 billion minus 1, I should say, and then just add them all up? Yeah, that would work, but it would obviously take twice as long than if I had two separate threads and one of them added the first half of all the elements in here and the other one added the second half of all the elements in here. Now, whether they start at 0 and 500 million, or this one does the even ones and that one does the odd ones, however you divvy up the work, it doesn't really matter for this particular example, but it could have an impact on your performance, okay? Bottom line is, if one does half, the other one does another half, and yes, I realize I have the same number here, but I round it off, right? This is like 4999999, okay? I'll leave that as a item for the comments, all right? Anyway, if you give each one of these threads half the work to do, it's roughly an equal amount of work, they'll both take about the same amount of time, which is half of the time, and that's the key here, than it would be for one of the threads to do all the work on its own. All right, so how do you do this sort of thing? Well, we'll leave spawning these threads as a subject for another discussion, but assuming they're both running, okay, what happens is they're both going to do their job. Maybe thread number 2 sums up all of its elements into a variable called T2 sum, and thread 1 will sum up all of its values into a variable called T1 sum, and then thread 1 at the end would say T1 sum plus equals T2 sum to combine them all into one total sum, and maybe it's a subroutine, it would return a value or something like that, okay? So that's the whole point of running more than one thread in the same application at the same time, this kind of action here, all right? Now let's see at one of the problems that could occur here. What if thread 1 finished before thread 2, and thread 1 did this before thread 2 had its total sum calculated, right? So there's a kind of a problem here. So thread 1 has to wait for T2 to finish. All right? This is a pretty important thing. Maybe in this particular example, thread 2 could do something like, after it sums its stuff up, there might be a flag over here. Okay, and maybe after it sums it up, thread 2 puts something like flag equals 1. Right? And then maybe thread 1, before it does the summing, in order to do its waiting, maybe what it'll do is it'll just go into a loop like this. Semicolon. So it'll just go around and around and around, waiting for this flag to become a non-zero value. So when thread 2 does this, it kind of like releases thread 1 to proceed. Now this is a pretty naive thing to do, okay? As you'll see, the compiler may decide that since you're reusing this variable over and over and over again, it might just read the actual value out of memory once to optimize this while loop, so that the variable stays in a register, and it'll simply say, is the register still equal to 0? If so, branch back to itself. And if it never actually goes back and rereads the value out of memory, this will be an endless loop no matter what the value, if it changes over time, right? So it turns out you have to say this, the volatile, you have to say, look, this integer is volatile. So this is something that we need to do in a multi-threaded app when we have variables that have values that could change as a result of some different thread that's running at the same time. So things like T1 sum, T2 sum, and the flag in this example, we need to let the compiler know not to try to help us right? It has to know not to optimize the reading of this flag away in this loop. So if it says volatile like that, then what will happen when the compiler generates the code for this loop, it will say something like, if it's an int, it would say something like load word. Maybe it puts it into x6 if this is RISC-V. And it would say, whatever from whatever address, I'll just abbreviate like that, represents the flag variable. And then it would say something like branch if it's equal to 0, x6, x0, back to like loop, and there would be a label in here like that, okay? If you do not have volatile, what will happen is the load word instruction would get optimized away and it would branch if equal back to itself, okay? That's why you need volatile on there. And that would be true for these for T2 sum at a minimum as well, right? Because obviously if this thing comes down here, it needs to know that it has to read the value of T2 sum at the time it does this addition down here, okay? Now let's look at another situation where you might want to use more than one thread, okay? Let's say you own a bank and you write some simple code here. You're modern, you got an internet-based bank or something like that. You have this main loop here that goes into an infinite loop that says, give me a request from the website. Right? So this is the logic that would handle your deposits and your withdrawals, right? So this request, let's just assume that the validation and error checking and all that is done in GET request here. This is not about, security right now. This is just about what do you do if you want to adjust the account balance, okay? So let's say you get a request, save it in a variable. You then say, I want to process this transaction for this account, and I want to adjust it by that amount, right? Maybe this will be a function that might look like this. The accounts, maybe they're all integers, and maybe the amount would be represented in a floating point number. Okay, if it's positive, it's I would argue it's a deposit. If it's negative, it's a withdrawal. All right. So how does that then work? You would simply say, well, give me the current balance for this account, start in a variable, add on the amount of the transaction, and then set the net balance to the new value for that same account. All right, so this would work fine and dandy until you run it with more than one thread. So why will this go wrong with multiple threads? Well, let's say you have two threads running and they're both waiting for requests and they both get one at the same time. Maybe your wife or your kid or something has your credit card, or I should say your debit card for your bank, and you're logged on to the web server and you're maybe paying your bills while your significant others are at the store or something like that shopping. So by coincidence, you both submit requests at essentially the same time, so that the two threads running on the bank server both get a request, start processing it for the same account at roughly the same time. When it gets down here, what's going to happen is, let's look and see what happens in, let's say thread 1 gets your deposit that you might be putting in online. So you're going to have like a plus $100 or something. And thread 2 gets the information about a card swipe at the store where they spent maybe $50, right? Well, if both of these happen at the exact same time and your current balance is, let's just call it X, all right? They both come in here and they both get balance at the same time for the same account. Both threads are going to consider the balance to be X. One of them is going to add 100 and store that sum back in there, which would be X plus 100. Okay, maybe that would be for thread 1, right? Because it gets this request. And because that's happening at the same time, thread 2 is going to get X. It's going to add a negative 50. And thread 2 is going to store X minus 50. Oops. That would even be worse, right? X minus 50 into your account balance. Now, if it happened in this exact order, what would happen is the balance in the end would be X minus 50. Maybe the bank would appreciate that, but you wouldn't, right? Because this whole deposit would have been ignored. All right, because it would have been overwritten when it wrote X minus 50. What you really want is X minus 50 plus 100 to be in your bank. Okay, so this is flawed if it's running with more than one thread. So how do we then solve this problem? Well, this idea of waiting and then going again kind of comes into play here. So let's first look at a naive approach using our simple flags. So maybe somebody somewhere creates a flag up here that would be like static volatile lock equals 0. Okay. And then inside here, we would put a simple little loop, just like we saw before. We say, while what? We want to wait for the lock to become 0. You have to just come up with a convention. Which values mean what? It doesn't matter. Is 0 mean wait, or does 1 mean wait, or that sort of thing. So what I'm going to do is I'm going to say while the lock is not equal to 0, I'm going to spin in this loop forever. If I see the lock become 0, aha, I'm good to go. So I'm going to say lock equals 1, so that anybody else that comes along and the other thread that comes along knows to wait while I'm doing this down here. And when I'm done, I can say lock equals 0. Okay? Now, at first glance, this might seem okay, but it's not. Okay? All you've done is relocated the same problem you have here into this while loop up here, right? As long as you can look at the lock value, ascertain that it has become 0, and then set it to 1 kind of all at once, this would be okay. But that's not what's happening. What does this bunch of code really look like if we looked at it in assembly language? If you look at it on, say, a RISC-V machine, what would really happen inside here, right? So let's look at this. We'll just jot them down over here. It may look something like this, for example. Maybe it'll say load immediate X7, put a 1 in there, okay? And then maybe it'd say a load address X6 with your lock, the address of the lock, okay? Then maybe we would say what? We go, then this would just get us set up so we can go into our loop, right? So maybe we'd have a label loop. And in this loop, we'd say what? What do we got? Volatile. I didn't give it a data type. Int. Okay. So what would we do in here? We would say load word. What? Some register, maybe X20. What? We would want to get the value of the lock, right? So we would say X0 off of X6, right? Then we would say what? If the value is not 0, I need to keep waiting because someone else would have set it to 1, right? So branch not equal, what, X20, X0, comma loop. Oh no, I'm running out of room here. Then what happens? You would fall out of this thing. If X20 ever was equal to 0, the loop would exit. Then we would want to set the lock equal to 1. Well, that's why we did all this up here. So we could say, then store word, we could say X7 into 0 off of X6 like this, all right? So now we have this loop with the lock equal to 1. The lock equal to 0 would simply be a store word like this, right? But the problem here is this loop. So what happens is, what we're doing is we're looking at the value in memory here. We're ascertaining whether we can go or not. And if the answer is no, we come back up to this loop here. So the problem is the window of time between the time we load it and think about it and then change its value is the same problem we had here. Because what if two threads come in here at the same time? And let's say lock is currently 0. You just started up your server. It's the first time of the day, and 2 transactions come in at the same time. Same scenario we had up here. Both of those threads are going to come down here and do every one of these instructions at roughly the same time, right? Because they could be off by 1 or 2 instructions, and this problem would still occur. As long as one of the threads comes along and loads the value of the lock variable over here into its X20 register, and it's starting to do the compare, and maybe the other thread comes along, loads the copy of a lock variable into its X20 register. The first thread says it is 0, so I'm going to fall through down here, and he changes it to 1. While the other thread comes down and asks, well, my X20 also has a 0 in it because it was read before thread 1 would have modified its value. So it too then stores a 1 into the lock variable, and both threads then proceed down here to cause the problem that we looked at before. So the problem really, you know, we can take it out of here and move it into here, but the problem remains. The problem is this right here. These 3 instructions, if we had a way to do all this in one single instruction, we'd be fine. So let's distill this down to just the basics of our concern. We have a variable of some kind that represents the lock, and it's stored in memory somewhere. We have some code here that we use to acquire the lock. Okay? We then have code here. This is what we call the critical section, our critical region. And then we have the release lock. Code down here. So we can ignore the bank and all this other stuff. We know that we need a solution for the acquisition of a lock, the releasing of a lock, so that we can write code such that if we have a multi-threaded program, only one thread at a time is allowed to execute this critical region of code. Okay, so here is our lock and our unlock functions that we're going to use, all right? Now, in order to use these, it's going to use this function up here called AMOSWAP, atomic swap. That's what that stands for. This is a RISC-V name, okay? Turns out other CPUs have names like test and set, compare and swap, and you know there's other, every vendor has its own way of doing this, okay? So this is the logic that's used in RISC-V, okay? And that's the name of an instruction. So this is really the pseudocode of a machine instruction. This whole thing happens in one single instruction, and we'll see this is why we now can use our simple loops trying to set and clear these lock flags. All right, so let's think about this for a second, how it works. This has to work in all cases. So let's look at a difficult case, right? Let's say you have a system that has more than one socket. It has 2 physical CPUs, and each CPU has a couple of cores, okay? So there's multiple threads running on each of these sockets, potentially running the same program, okay? The only thing we really add that we didn't have before is this one new signal called RMW. Sometimes it's called ILO. It depends on the different manufacturer of the chips. This stands for read, modify, write. This stands for interlocked operation. Okay? They all do the same thing regardless of the name. All right? So how does this really work? Now remember, if you have more than one socket sharing the same memory, you have to have something in here. I'll put an A right here that arbitrates and decides which socket gets to talk to the memory at any given point in time. They're all going to be fetching instructions out of it. They're going to be loading data out of memory and storing data back into memory. They can't do it at the same exact time. So what happens is the arbiter logic says it's your turn now to do one memory transaction. Maybe this socket over here will read some data into some registers or something, and it'll then do some processing. While it's doing that, this other socket might say, I need to fetch an opcode or something. So it'll say, I need the bus now. The arbiter will say, okay, no problem. It's your turn. And it'll read some memory and it'll load up some instructions into its cache or something like that. Okay? Again, that's the purpose of the arbiter. Now, this signal here is connected to the arbiter. And the way it works is anytime the arbiter grants access to one of these sockets, on behalf of one of the cores inside the socket, okay? Because this propagates all the way inside into each of the cores too, right? Whenever the arbiter grants access to the physical memory bus for any one of these sockets, that socket at that time can assert this signal and say, hey, I'm going to do more than one thing. So don't just take the one transaction and then give the bus to some other socket. And this is the key. This you can't do in software, okay? You have to have a wire over here to tell the arbiter that you're going to do two transactions, and they have to take place uninterrupted, undivided. No one else can sneak in here and read or write into the memory while those two transactions are taking place, okay? So this kind of simplified pseudocode for what happens when someone wants to set this lock or read the lock value and change it, okay, works like this. So it says, you know, I'm going to assert the RMW so that when the bus arrives, you know, when the arbiter gives access to the bus here, okay, it'll be a 1. And this is kind of hard to show in C or C++ because this is all done in hardware, all right? All this is one single instruction in hardware. But this is basically the order in which these operations are done and logically what will happen as a result of it, okay? So we set RMW to 1, we do some stuff, we set RMW back to 0. So that's the key here, right? So inside here, this is atomic. One single bus tenure between one of these sockets and the memory will allow both of these to happen as if it was one single atomic thing, okay? So what are they? Now let's look what happens here. We got this AMOSWAP, and we have here's my volatile int reference. So this represents the lock. And this I variable is the value we want to put in that lock, right? That's like we want to set the lock to 1 if it was 0 before, kind of a situation, all right? So the way the AMOSWAP works on a RISC-V machine is we have a temporary variable. It'll read the current value of the lock. Then it will say, put the I value into that lock, okay? It undoes the RMW thing for the arbiter, and then it returns S, which is what the lock was before it was modified. Okay, now this isn't quite the same thing as waiting for the lock to become 0 and then setting it and so on. But this is what we can use to make that happen. Let's look and see what happens down here. If we want to grab and acquire our lock, what do? We call this lock function, we pass it a pointer, or a reference, we should say, to the lock variable. Here's our while loop in here now. We AMOSWAP that lock, we want to set it to 1. And if this thing ever returns a value that's not 0, we loop around and around and around, do it continuously. So let's think about this. So what happens in the order of operations here? If I call lock in my program and the lock is not yet set, so this M variable, I'm passing it my lock, and my lock is currently 0. Okay, so let's walk through and see what happens there. We will call AMOSWAP, we give it M, which is a reference to a variable whose current value is 0. And we give it a 1 for the I over here. Okay, so what is it going to do? It's going to assert an interlocked bus operation. It wants to do an RMW, a read, modify, write operation on the bus. The arbiter gives it access. Okay, what's it going to do? It's going to say, tell me the current value of the lock and store it in this variable. I'm going to call S. And in this scenario, I said it would be 0, so S will be 0. And they'll then say M equals I. And I passed a 1 in for that, so it'll set it to 1. It'll tell the arbiter it's done. And it will return S. And S in this scenario will be 0, because S is the value that was in the lock before it was changed. So this while loop now, return value of AMOSWAP is 0. The while loop is done. Lock returns. We've acquired our lock. We then can execute the critical region of the code, and then we can call unlock, which is essentially just sets the lock back to 0. Okay? So let's say we have an app It's running along. It wants to acquire the lock, but it's already in use by another thread. So in that scenario, our M would have been set to 1 already when that thread enters in this lock subroutine here, and it starts to try to acquire it. What is that one going to do? Well, it's going to call AMOSWAP. It's going to pass it the reference to the lock. Remember, the lock is currently set to 1 in this example because some other thread holds that lock. It's already busy. Okay, so say we want an atomic operation. It's our turn, so we're going to say, tell me the current value of the lock and store it in S. That will be setting S to 1 in this example. It will then set M equals I, which is 1. It's already 1, so that will be no change. Tell the arbiter we're done. Return S. This will have returned to 1. 1 is not 0. It'll call it again. Okay, so it'll do this repeatedly until someone comes along and sets it to a 0 in here. Because every time you go through here, this will return the value of the lock before it's been updated and set to, in this case, it'd be a 1. Okay? So essentially what this is doing is it says try to set M to 1. And if it's already 1, try and do it again, and again, and again, and again, until we succeed in changing M from 0 to a 1. Then and only then do we know that the thread has acquired the lock. Because the thread has to see it go from 0 to become 1 in order to know that that specific thread succeeded in acquiring that lock. Now let's take a quick look at the Atomic Memory Operations section of the RISC-V User Level Manual from 2020. This is version 2.2. It's open source, free online. I'll put a link to this below the video and in the course website if you want to follow along at home. This is section 7.3, and inside here you see this is the AMOSWAP instruction. You can see there's other ones. There's add, and, or, XOR, max, min, and these are just variations of the same sort of a thing. Rather than saying, hey, read it and then swap the value, you can read it and add a value to it, or and it with, a bitwise and. You can do all these other things as well. And in certain applications, these other operations are preferable, okay? Let's keep it simple. We're just talking about the swap right here. Now, if you scroll down a little bit, you see an example in here on how to use it. You'll recognize this is roughly our algorithm that we've been trying to sketch out to make work, okay? So how does this thing work? You say load immediate, the value 1 into temporary register 0. And you'll see that temporary register 0 is the value we're going to try and store into the lock, okay? Now, before you enter into this code, register A0 should be preset with the address of where the lock is in memory, okay? So how does this thing work? You run amoswap.w means that it's a word, okay? It means it's a 4-byte integer value. AQ means you want to acquire a lock. Down here we'll use it again to release the lock, okay? Now these are there to allow optimized versions of processors that might actually try to execute instructions out of order if doing so would make it run faster, okay? They need to know whether you're acquiring a lock or releasing a lock in order to not screw up this code, okay? So, yeah, we're not going to get into the details of that. Just suffice it to say, some fancier CPUs need to know the difference between an acquisition and a release. And we're going to use T0 for both of these operands here. Okay? Now, if you look at the binary encoding in this instruction, there's no room for an immediate offset. So when you encode the address, the only thing you can really put over here is 0 off of A0, okay? And the notation that you use for this specific instruction is to not put an offset in here at all right? It's kind of wonky, but that's what you get when you use this particular instruction. That's what the assembly language encoding looks like, all right? So these T0 arguments, what are they, right? Well, those are, if you look up here, the destination register and the source register here, okay? RS1 here is the address, okay? In that example, that was A0. The T0 is used for both the destination and the source in this scenario, okay? Now, if you read through here, you'll notice that it says, like, I'm going to load the data value from the address in RS1, okay? It's going to be placed into the destination register. Then it's going to apply the operator. In this case, we're not going to do anything. We're just going to swap it using the value in RS2, all right, and store that value back into the address at RS1, okay? So what we're going to do is we're going to take the value in memory at this address here. We're going to store it into the register RD over here, and then we're going to take the value in RS2 and we're going to store it in memory where the address points in RS1, okay? So this code is kind of optimized. It only uses one register, all right? By setting this thing to a 1 up here and using it for both the destination and the source, what happens is if the memory word at the address in A0 over here is A0, then when this instruction's done, T0 will have that 0 in it. A0, the address A0, the word that's in memory at that address, will be set to 1 regardless. It'll already be 1 and not be changed, or it'll be set to 1 because that would be the value that's in T0 at this point in time, right? Either way, the lock will be acquired, okay? T0 over here, if it is a 1, when this is done, it means that another thread already has that lock acquired. So we can then ask, is T0 not equal to 0? Now, BNEZ is one of the pseudo instructions. What that really is branch not equal to T0 comma X0, okay? And then go back to the loop at this label here. So what happens is, if it got the lock, T0 changes to a 0. And then we fall into our critical section. And then we use it again to set it back equal to 0, okay? If it did not acquire the lock, the word in memory at the address in A0 will already be set to a 1, and therefore T0 will still have a 1 in it when this is done, and 1 is not equal to 0, so the loop continues, all right? So they went and optimized this down to only use one temporary register instead of using 2, that's all, okay? Now, as I said, the optimization logic for fancier CPUs need to know whether you're acquiring or releasing the lock. It's kind of an FYI that you put in when you encode this instruction. And by putting X0 in both of these, we're saying I don't care what the lock was, throw it away. That's your RD register there. And the source is 0. So what we're really doing is we're setting A0 to 0 no matter what, okay? And we're doing it with AMOSWAP only because we need to provide this RL, the release flag, to let the CPU know not to optimize the code in a way where this won't work, okay? Same kind of problems happen inside the hardware that does with smart compilers and stuff, right? As you optimize hardware and you start creating pipelines and things like that, or executing instructions out of order, you get really fancy. You're trying to save energy, you're trying to save time and everything else, but you increase the complexity, right? So as a programmer, you have to provide hints and tell it not to get in your way when you don't want it to get in your way, okay? So that's how you actually use the real instruction inside of RISC-V to implement what we call a mutual exclusion semaphore, okay? What we want to do is say this is mutually exclusive here. Only one thread at a time in the entire system is allowed to execute the code in this critical section. And you acquire a lock by doing this. You release the lock for other threads to start using it later on by doing this down here. So this is how we protect access to critical sections of code, at least on a RISC-V here, and in a more general sense, using a notion of a compare and swap or a test and set type of an operation. You enter into a loop waiting for the lock to become available, and then you acquire it. And when you acquire it, you have to do so in a single atomic operation. And this particular style of locking and unlocking for a single thread to access a critical region like this is what we refer to as a mutual exclusion lock or a mutual exclusion semaphore. Okay, lock and semaphore. Lock is a specific kind of semaphore. So use of the word, lock versus the word semaphore, what we're really doing usually when people speak of these things, semaphore is a more general term. Lock is more specific, okay? For example, if you use the ammo add instead of ammo swap, you can write a loop like this to acquire a semaphore that would allow something like 2 threads at a time into the critical section, but not 3 or more. It really depends on the needs of the application you're writing, okay? So you can mix and match these and do all kinds of stuff. Here, we only focusing on the simplest of all, which is mutual exclusion. Thanks for watching. See you next time.